Welcome to this session where we talk about principal stresses and principal directions. If you remember from the previous video where we were discussing about the stresses in an incline or on an inclined plane, then we mentioned at the end of the video that it might be possible to find an orientation for that infinitesimal cube where the stresses in that plane, in that kind of oriented differently plane, it's going to be contained only by the normal. So a pure normal stress there, we're not going to have any shear stresses or anything like that. So if I could draw this in a certain way, let's draw again our Cartesian coordinate axis, this one, to describe the idea, X, Y, and Z. Then I'm going to draw again my plane or inclined plane. Our situation here goes so that we're going to have a plane where when I cut it from the infinitesimal cube, the resultant stresses there they're only going to be normal stresses or a normal stress there. So the way you can see this is if you have an infinitesimal cube where, with all the stresses applied to it, as we have seen many times in the previous videos, kind of this sigma xx without taking into account the variation of the stresses, and to put just the principal ones, sigma y, y, sigma z, z, kind of take into account the shear stresses and so on. If I make this cut, something like this in here, I'm going to end up having some kind of inclined plane. So it is highly possible that when I cut this plane, I'm going to have a kind of a stress situation where the only stress or existing stress is going to be a normal stress. Remember when we have the peanut-shaped body that we made a cut, and this body had many forces or external forces applied to it. When we made, or when we introduced the plane cut here, or the cut plane, this one here, we had to somehow tell to the system that there was a right part, or there was a part that now is missing. And we did that by saying that there was going to be here a moment and kind of a resultant or average force. In this case, when I make the cut in the infinitesimal cube here, it's going to be more or less the same. That's why what I'm saying now is that when you make a cut, you can find a cut or a plane, oriented plane, where the only resultant stress is going to be normal stress. And we're interested in that situation where we are not going to have any, let's say, any shear stresses there apply. So just normal stress, which happens to be the maximum stresses we're going to find inside of the body. And that's going to allow us then to compare this maximum stress to kind of the yield stress or the maximum stress that you're going to have for your material there. And when you're in the presence of this situation, what you have here is the principal, or these are called the principal stresses. And when you find the directions of those principal stresses, that is called principal directions. Our main topic in this video is how to determine these principal stresses, so how to find out this plane where the principal stresses are located, and obviously, what are the principal directions. It's going to be a little bit kind of maybe hard to follow because I'm going to do certain derivations to find out how to get from the stress tensor that we saw previously, how to get these principal stresses. Let's start by something. So if I assume that there are not existent shear stresses there, I could say then that, remember this force, this stress T that we used in the previous video? Some heads up about the previous video. I was missing a 2 here. Of course, this corresponds to this one. So please check this out. Then if I consider that there is only going to be a stress represented in the normal direction, this means that this is not existent here. So this stress T now, in my case, can be represented by T equal to sigma n. Definitely, because if I have the plane and like this one, the area, and this is going to be aligned with the sigma normal, and this is going to be equal to the normal stress in the unit, in this unit vector here that represents the normal direction of coming out of this plane. Then if I said that this is the only thing or the only stress I'm going to have in this case, then change the color. It's easily said that the components of this stress represented in my Cartesian coordinate system is going to be something like this. Then Ty equals to sigma m, and Tz equals to sigma times n. So by multiplying these vectors, deleted here, this vector sigma, that is this normal stress, with the direction cosines, then I can get kind of the transformation between the normal plane and my Cartesian coordinate system. There is another way I could write this. So utilizing the matrix representation of the Cauchy stress formulation or formulas, I could write this into this form, like this, in matrix form. This is going to be just exchanging T by the sigma sign. This is a stress tensor. Yx tau yz. Sorry. Tau cx. Let me follow this one. Tau xy, tau xz, sigma yy, and tau. And this is going to be zy, tau yz, sigma zc. Then times my direction cosines. Then one thing that I could do with this term here is that I could represent it as a matrix times a vector. So I can transform that left side of the equation into this, to a diagonal matrix. It's going to give me the same result, L, M, N. Great. Now what I'll do is to move the vector or the stress I'm interested in to the left or to the right side of the equation. And I'm going to combine them together, meaning that I'm going to have my stress tensor here, tau xy, tau xz, sigma yy, tau yx, tau yz, tau zx, tau zy, sigma zz. Minus my normal vector, the one that I want to find. We continue this. I have two common terms. Then I could rewrite the whole equation into this, or like this. Sigma xx minus sigma tau xy, tau xz, then tau yx, sigma yy, tau yz, tau zx, kind of rewriting all the terms again. Minus sigma here, minus sigma, times, this has to be equal to 0. L, M, N. This has to be equal to 0. Then, as I know, usually one of the known variables in the whole, most of the problems is the stress tensor. So my problem here consists on finding out what's the value of that normal stress. And if I already have this equation, I know most of the terms of the stress tensor. So I know the terms in the stress tensor, and I need to find the value of the normal stress. I need to solve this equation, and this equation might have a trivial solution where how to make this 0. Basically, the first solution that you might think of is, okay, if I want this equation to be equal to 0, then one of the first attempts would be that, okay, what about if this is 0? Can this be equal to 0, this vector here? And that would be the trivial solution of this problem. However, there is not a trivial solution because we know from the previous video that there is a relationship between these direction cosines. Remember that we said that direction cosines are kind of related by this formula, square plus m squared plus n, meaning that this can never be 0. Hence, there is not a trivial solution for this equation. However, there is a non-trivial solution where I would say that this part of the equation, this matrix, basically has to be 0 in terms that the determinant of the matrix has to be 0. And that's going to be the determinant has to be of the matrix here has to be equal to 0. And that's going to be my non-trivial solution. Then I need to start working with the determinant of this matrix and make it, I'll try to find out how to make it 0. Let's see. This is where the derivation of all of this becomes a little bit lengthy, but bear with me. To calculate the determinant of this matrix, I will use kind of the simple rule to do this. You have done it before for sure. I will write the same matrix, but I would add to the right side the first 2 columns of the matrix. That's going to be something like this. I will have this term here. We'll write them all. Then this side here is going to be tau xy, sigma y minus sigma, tau zy. Then in here, I'm going to have tau xz, tau yz, and then sigma zc minus sigma. Then I will copy these two columns in here. Yeah, good. And then I will calculate the determinant of the matrix by using these, let's say, this nice rule here. I will multiply these terms. Then I will add the multiplication of these terms. Then I will add again the multiplication of these terms. We write it like this. This one here, yeah, to make kind of an arrow to represent the direction that I'm using here. These are going to be sums. Then I will subtract the inverted diagonals here. But let me do these ones first. Let's see. The first one would be, start working with this, is sigma xx minus sigma times sigma yy minus sigma times sigma zc minus sigma. This is a magenta color or diagonal plus the yellow diagonal. That's going to be tau yx times tau xy times tau xz, yeah, plus the violet diagonal. It's going to be tau zx plus tau xy times tau. This is not plus, this is times yz. Perfect. These are this is my sum. Now I need to subtract the inverted diagonals. Minus, this is going to be my first diagonal here, which is going to be negative. This is going to be my second diagonal here, negative, and then the third diagonal here. Perfect, let's do it. Minus the magenta diagonal here is going to be, going to open parentheses maybe. No, that's fine. It's a multiplication, so I need to keep track of the signs. Tau zx times sigma yy minus sigma times tau xz minus, yes, the yellow diagonal, parenthesis, sigma xx minus sigma tau. This is the reason I should write better this. Zy times tau yz. Yes. Minus the violet diagonal, inverted diagonal, tau yx times tau xy times sigma z minus sigma. And this has to be equals to 0 here. Nice. Now it's a matter of starting grouping terms and simplifying this equation to see what thing comes up. Okay, let me have it here. I'm going to split this into, let's say, this term here, the first one. sigma xx minus sigma times sigma yy minus sigma parenthesis sigma zz minus sigma. This one here. Let me see what brings in here. This is going to be equal to what? We'll work with these first two terms. Yeah. Then I will have sigma xx minus sigma. And then this term, the multiplication of this term is going to be parentheses sigma yy times sigma zz minus, how to put it? Yeah, sigma times sigma yy. Yep, plus no minus sigma zz. Should I write it in the same fashion that the other one? Yeah, it's better. Sigma times sigma zz. Yeah, and then these two terms would. Sorry, the video froze and I missed part of the explanation I was doing here, but I'm trying to, okay, I can put it together again. And hopefully I'm going to start from this part that where the video froze. Okay, so we were in this stage and we said that we were going to have also this term here, plus sigma square. Yes. Then I said also that I will need, okay, I need to multiply these two terms now. They are in the parentheses in here. That is going to be then, I'm going to write from here, sigma xx times sigma yy, yep, sigma zz minus, yeah, sigma times sigma xx sigma yy. Is it minus? No, it has to be minus in here. Minus sigma xx sigma z. Yeah. Then I will have plus. Well, let me write it like this. Yeah. Although I should have written this in the inverse direction, but it's okay. Then I need to multiply the sigma times the other elements that we have there. Let's go, let's do it. Let's see, we have then, should I leave it as it is? Okay, let's do it. Minus sigma yy, sigma zz. Yes. Then minus times minus is plus here. It's going to give me sigma squared sigma yy. Yes, plus minus times minus plus. This is going to give me sigma squared sigma zz. This and this is going to give minus sigma power 3. Well, let's group some similar terms here. The first 3 terms, we cannot do much, I think. Let me see. Yeah, the first term is going to be sigma xx times sigma yy, sigma zz, then minus. I'm seeing here that I have these sigmas that I could group together. And that's going to be sigma that multiplies, open parentheses here. Yep, sigma xx, sigma yy, plus sigma xx, sigma zz, plus sigma yy, sigma zz, close parentheses, plus I have also these terms, this sigma square here. Then I will have sigma square, open parentheses, sigma xx plus sigma yy plus sigma z. Yeah. Finally, minus sigma to the power of 3. Okay, this is what we get. This one here, this is the result. Just from the first term. This one is this one here, and then this is the result there. But now we have the left or the rest of the equation. All what we have here. Let me put it in this. I will write it down like this, black. I will have, let's see, where we start with. Yeah, I could, well, first, red. This term here, using the reciprocity of shearing stresses, is going to be equal to this term here, meaning that I could write this as 2 times tau xy, tau x, put it in order. It doesn't matter, but just wanted to put it in order. Yz times tau xz. Yeah, it's the same there. Then minus, to have a big plus here, minus. Let's see what I have in the rest of the terms. This one is equal to this one. These two, I can consider them equal, and then this one are equal. Meaning that I could say, yep, let's do this. Let's first say that this is minus tau xz square times sigma yy minus sigma minus tau yz times sigma xx minus sigma, this is square, minus, okay, the other one is going to be what? Tau xy square sigma z minus sigma. Good. So these are kind of the two parts here. It would be good. It would be good also to open up these parentheses here, because I have these sigma symbols here. For sure, I'm going to need them. So I'm going to write everything from as it should be all together, what I have found until now. My solution of my equation, I'm going to have sigma xx, starting from this one here, sigma yy, sigma z minus, let me write this one, yeah, sigma times sigma xx, sigma yy plus sigma xx, sigma z plus sigma yy, sigma z plus sigma square, open parenthesis, sigma xx plus sigma yy plus sigma z, sigma power of 3 plus 2 tau xy tau yz tau xz. Now you see that it was pretty convenient to have this rotation equilibrium where we found out that there is a reciprocity on shearing stresses. Well, we have this one, then minus tau xz square. Yes, minus. Actually, let me open up this right now, because I will have to write it again. Then this one is multiplying tau yy minus square times sigma. Yes, this whole thing here became these two terms here. Yep, good. Let's do it. Let's keep working with this. Minus, but this should be plus, isn't it? If you notice that I make a mistake on one of the signs, just keep, just be aware that it can be any mistakes here, or a mistake can be here. Okay, let's continue. Minus tau yz square times sigma x plus tau xz, yz, sorry, times y, times sigma minus this tau xy square times sigma zz plus tau xy square sigma. Yes, we are getting closer. Now, I could, when I group all these terms, so I will try to group them. I noticed that I have the sigma, that's the value I want to find, is represented by a polynomial of third degree. This one here. And so what I'll do here is I will try to group them into kind of each one of these the degrees of the polynomial, starting for the first one. So minus sigma power of 3. Then I will have plus sigma square times, yes, perfect. Then I will have minus sigma that multiplies, we'll write the first one. There is this one, xx yy plus sigma xx sigma zz plus sigma y. Sigma yy sigma zz. Good. No, it doesn't close here. Then that's going to be subtracted to the other terms I have here. Let me write them into order, in the order of x, y, z. Let's start with which one? Let's see, what is the first one here? X, y. We could write this one here. Minus tau. Yeah, y z squared sigma x, x. Yeah, let's start with this one. Oh, sorry. Sigma, because I'm not using this one. I am using these ones here. This one, this, and what is the other one? This one here. These three terms. Okay. So now let me write it in the same order of appearance. So xz squared minus tau yz squared minus tau xy squared. Yeah, minus because with the other minus or the other minus, it makes it itself plus. But still, I have the other terms that are kind of independent terms. And this is going to be represented by, let's see, plus, where they are. Yeah, definitely, I'm going to have the multiplication of these three normal stresses. Yeah, times this one. Then I will have, yeah, this one here plus 2 tau xy, tau yz, tau xz. Then I will have these three ones here. This, and this one here. And that's going to be minus. Yeah, should I write it in the same fashion again? Yeah, let's put it in this way. Tau yz squared sigma xx minus tau xz squared sigma yy minus tau xy squared sigma zz. Yeah. And this has to be equal to 0. Now, this part, I'm going to write it now, kind of, there is certain steps that we could use to simplify this equation. And I will jump those steps and I will write down kind of an abbreviated form of this equation. So this is a third degree polynomial equation. I will start by writing it like this, blue one. Yeah, it's going to be that sigma 3, you can verify this at home. Sigma 3, sigma to the power of 3 minus, I'm going to call this term I1 sigma squared plus I2 sigma plus I3 equal to 0. So this is the same as this one. Where these kind of terms here represented here, I1, I2, and I3 are something that is called invariance. Okay, let me write it. Invariance. These invariants are mentioned or are named in that fashion is because they don't vary. You know, they're always going to be the same. Good. Let's see. I1 is going to be equal to what is multiplying sigma square. And what is multiplying sigma square is the sum of the normal stresses. It's going to be sigma xx plus sigma yy plus sigma zz. I2, when you come up to the simplified form of these terms, or what is multiplying sigma, that's going to be represented by the sum of a few determinants, matrix determinants. It's going to be represented by this determinant here, sigma xx, tau xy, tau xy, sigma x x plus the other one is sigma y y tau y z tau y z sigma y y plus this determinant here sigma z z tau x z tau x z sigma z z. You could choose to use this form here. That's recommendable to use it because as you know that the invariants they are not going to change no matter what, then you can keep track of them and kind of perform other operations on your infinitesimal cube or rotations. So this is important to make. Of course, you could keep it like this one or the long form that is represented in all of these red equation, but this is the simplified version of that. And we're going to have the third invariant here, and that's going to be represented by, actually, it's going to be represented by the determinant of the stress tensor. Something like this. It's amazing. Yx, Zx, tau xy, tau xz, sigma yy, tau yz, tau z, y, sigma zz. Yeah. There you go. Again, the stress tensor is appearing here. Then what are the kind of the principal stresses here? Those stresses, you have to take into consideration this equation here. When you find a solution for this equation, meaning that you find the three roots that solve this equation, this is going to give you three real roots. And these three real roots are going to give you three stresses, namely sigma 1, sigma 2, and sigma 3. And these are going to conform, or these are going to be your principal stresses. Now, there is an important naming convention for this. And that naming convention says that sigma 1 has to be chosen that one that is the larger of all of them. And sigma 2 is that one that is larger than sigma 3. And this is the order or the convention you have to follow, because this is going to help us to construct later the Morse circle and to see how these normal stresses appear in the Morse circle, in the 3D Morse circle, and then the corresponding shear stresses, even though we said that these principal stresses are on a plane where there are only normal stresses, but they are all going to be kind of internally in the body. They're going to be also shear stresses, and we can find out what is the relation between them. Then you have to keep this. So whenever you find these three roots of this equation here, you have to order them from larger to smaller. And the larger one is going to be sigma 1, the middle one, sigma 2, and so on. And the smaller one is going to be, smallest one is going to be sigma 3 in this case. Now that we found the principal stresses, let me write it down here. It's necessary to know how is this plane oriented. So because we now are kind of working blindly. So we know that we can find a plane where there is only acting normal stresses, but we don't know yet what's the orientation of that plane. We need to know that. And for that, we are going to kind of make use of the direction cosines to find out what are kind of what's the orientation of this plane. And the orientation of this plane is going to give us the principal directions. Here. So it is said that to find the principal directions in this case, you have to take our first equation here, this one, not the first equation, but one of our first here, and substitute sigma 1 in here, and in here. And then you can solve this again, this determinant to find the zero value. And the results that give you, is going to give you L, M, and N. However, and then you do that with sigma 2, and then you repeat the procedure with sigma 3. However, I'm going to give you kind of a straightforward formula to calculate those principal directions. And that formula is based on, again, on this stress tensor. Let's write the first one. Here. I'm going to have here, yes, tau xy, tau xz. We have tau yx, sigma yy minus sigma. Let's assume that I'm taking the first principal component, principal stress, tau yz. And then here, tau zx, tau zy, and sigma z minus sigma 1. From this one, I'm going to bring I'm going to construct 3 quantities. And these quantities are going to be based on internal matrices of this big tensor. The first one is going to be, let me write here, A1. And A1 is going to be meaning to affect this term here. And it's going to result from calculating this submatrix here. Meaning that this is going to be represented by the determinant of this matrix here. So it's going to be sigma yy minus sigma 1, yeah, tau zy, and here tau yz, sigma z minus sigma 1. Yeah, perfect. The second one is going to be to calculate this one, or refer to kind of to this column. And the second one is going to refer to this column. And it's going to be to calculate, or we're going to use this term here. I should write it. Let me copy this again. It's going to be better. This one. Try to copy it. Sometimes it's difficult. Okay. I think I got it. Copy and paste in here. And I will delete this one here, this, and these two. Remove this one. Now let's talk about this column here. And it's going to be by applying in these form terms that they're going to form this next submatrix. Nope. B1 equals to, again, it's going to be actually negative tau xy, tau zy, tau xz, yeah, then sigma z minus sigma 1. Good. Then the other quantity, C1, in this case C1, yeah, copy, then paste to put it here. It's going to be referring to, you get rid of this yellow, to this column here. So we'll have these terms, or working with these terms. They're going to be C1. Sorry about my bad pronunciation. It's going to be tau xy, sigma yy minus sigma 1, then tau xz, yeah, then tau yz. Perfect. Then finally, the direction cosines using this formulation is kind of going to be resulting as this. L is going to be A1 divided by the square root of A1 square plus B1 square plus C1 square. But just remember that this kind of referring to sigma 1. So we have to repeat this for sigma 2 and sigma 3. Then we're going to have M, because yeah, definitely sigma 2 and sigma 3 are going to have different orientations. So these three principal stresses are going to form an orthogonal basis of stresses here. So it could be something like this. So that's why we're going to have three directions, three different directions. M is going to be B1 divided by the square root of this, which is a length, C1 square. And you know, you can infer now that N is going to be equal to C1 divided by the square root of this term here. And there you go. Now you have the directions, or a way to calculate the principal directions utilizing the stress tensor. Important to mention is that if you're going to use what I recommended also here, or mentioned here, that you could calculate the principal directions by substituting the values of the principal stresses one by one, of course, kind of in this term, and solving for the determinant of this matrix, you have to be aware that this condition here has to be fulfilled, meaning that your results have to fulfill this condition here. So meaning that it might be a little bit kind of working a little bit more, but you know, this is a nice way to calculate the principal directions. Or you could utilize what I have just mentioned here, that, you know, making use of the stress tensor and what I've just said and the submatrices, then you can find these quantities. And per each one, you're going to have kind of there. If I call this one M1 and 2, you're going to find out also L2, M2, and N2, and here L3, M3, and M3. And this is going to give you the direction of this orthogonal basis for the principal stresses. This is just an arbitrary drawing of it. And yeah, we'll stop the video now. I hope you get the idea of finding the principal stresses and principal directions. It's a little bit laborious, you know. We had to do a lot of mathematical operations, but they are pretty simple. It's a matter of simplifying equations. And again, if you see that there is a sign that shouldn't be there, you know, should be instead of a plus, should be a minus sign, well, just let me know. But yeah, this is it. Yeah. Next, we will continue with the other topic referring to this part, that is stress and strain. So we will continue with strains. And then finally, to end up with the relationship between stress and strain, kind of how to relate both those quantities there in 3 dimensions. Yeah, thanks for watching. Then hope to see you soon in the next video. Bye.